kind of want to try to push it exactly horizontally, so you're going to get most of your forces going in. You certainly don't want to push down on it while you're pushing that. Okay, maybe you could kind of push up. Pushing up actually really helps a little bit because it eliminates the normal force and decreases friction. So it's a great way to, if you can kind of push up a little bit. But anyway, or have somebody else kind of pull it up a little bit. But this definition is great when they're both in the same direction. When the force and the displacement are both like parallel vectors. Okay, because technically displacement is also a vector. Okay, but as we deal with more complex situations, we have to have a slightly more complex formula, okay? And the formula is that work is equal to the force that is in the same direction as the displacement vector. So it's this guy right here, which we will call Fx. It's the component of the force that is in the direction of the displacement, okay? So we've been dealing with this forever. What is Fx as it relates to theta and F? Anybody? Fx equals?
Magnitude cosine theta.
Magnitude cosine theta. So it's F cosine theta. And the work is F cosine theta times d. Or we could say, normally it's sometimes rated as FD cosine theta. FD cosine theta. All right. What's more is that if, since these are all vectors, if I have a vector here and this is a vector, then we say it's the magnitude of vector F times the magnitude of vector D times the cosine of theta. All right. With that in mind, let's recall one of the uses for the dot products, and actually kind of finally related back to dot product. We said that the dot product between vector A and vector B was AX BX plus AY BY. That was one of our formulas. The other formula that we had was that theta is equal to the inverse cosine of the dot product divided by the product of the magnitudes. Is that somewhere in your notes maybe? Mm-hmm. Okay. I want to take this equation and manipulate it slightly. Okay? So manipulating now. First, take the cosine of both sides. So cosine of this side gives us cosine theta equals cosine of the inverse cosine is just left back where we were. So vector A dot vector B divided by magnitude A, magnitude B. Jeremy and John, are y'all kind of cluing in from time to time? This is amazing stuff here, I'm telling you right now. All right. Last step here, almost. I'm going to multiply both sides, magnitude of A times magnitude of B. All right. And so what I do is I get A dot B is equal to magnitude of A, magnitude of B, times the cosine of the angle in between them. So this is another form of, another way of writing A dot B. We could write A dot B as AX times BX plus AY times BY, or you could write it as the magnitude of A times the magnitude of B times the cosine of the included angle. Okay? Now, magnitude times the cosine. Look over here, and you see that's exactly what we've got going on here, right? Look at that. Magnitude of a vector, cosine of the included angle. Okay? So that is what has led physicists to write this. They say that the work in its most general form is equal to the dot product of the force vector and the displacement vector. Let me say it again, that the work done is equal to the dot product of the force vector and the displacement vector. Okay? Which you could write it as ax, bx, ay, by, or you could write it as the magnitude times the cosine of the angle. Okay? But that's kind of an interesting thing. The advantage here is that this will work every time. It doesn't matter, you don't have to be completely horizontal, okay, and pushing something. You could have a displacement maybe at an angle. Maybe we're pushing this thing, we start here, and we push it up here. It's at, you know, it's like on some sort of ramp, like there's the displacement vector, okay? But the force that I'm doing on it, I'm kind of maybe pushing on it, you know, like this, as it's moving up, or something like that, okay? So my force vector looks like this. We can calculate how much work I'm doing on this object to move it up by taking the dot product of my force vector and that displacement vector. So some kind of interesting stuff. For our purposes and the problems I'm just about to show you in 1 minute, we're really just going to need this one right here, where everything is just nice numbers, not necessarily vectors, but they're all the magnitudes. The magnitude of f, the magnitude of d, and the cosine of the angle between them. That's all they're going to throw at you. If any of y'all end up taking physics in college, or wanting to study anything in engineering or math or science, I have never seen anybody explain dot product this well. So you're welcome. Anyway, but for the rest of us, let's go ahead and look at problem number 3 and number 4 on that homework. This one says a gardener pushes a lawnmower with a force of 20 newtons downward and to the right, as shown in the figure below. The angle the handle makes with the horizontal is 66 degrees, and the lawnmower is moved 51 meters. So we would say that the displacement, D, is 51 meters. I could say the magnitude of it is 51. The magnitude of vector F is 20 newtons. All right? Find the work done in joules, okay? And I'll leave it to Ms. Withers if she wants to show you how you can convert meters and newtons to joules. But here's our formula that we're going to use. The work done is the magnitude of F times the magnitude of D times the cosine of the angle in between them. So, class, what's the magnitude of F? 20. I can put it right there, sure. Magnitude of D. 20 newtons. That just looks bad. The N makes it look like a metric sign. Or yeah. So 20 times 51 times the cosine of 66 degrees. That's equal to the work done. A Newton meter is a joule, by the way, but 20 times 51 times cosine 66, enter. $414.87. Joules, done. All that for this. Yep, that's fine by me. Any questions? Make sure you have that formula. Yeah. It's a great one to take care of on Alex for your topics. If you can find it, Additional trigonometry topics is where we are. All right, shopper pushing a grocery cart with a force of 55 newtons. Down to the right, showing the figure below, the angle makes a handle 37 degrees with the horizontal, and the cart moves 19 meters. So you're telling me that all I have to do is multiply those two numbers and the cosine of the angle in between them? Yes. F times d times cosine theta. Got it? Great. This next problem involves a few more steps.
Oh, okay. I see.
Alright? Yeah. Alright.
Why did it go backwards with like?
I don't know. I'm the one who chose the order, so it's my fault.
Oh, wow.
I'm sure I was following some sort of order. Normally problems like this are easier because it's just sort of straightforward, and the ones that are like the context with the pictures and the people doing
Yeah.
stuff are like more complex, but you know, whatever. You should be able to see some similarities between this and the other ones, at least conceptually here. So we're going to look at this, and then we're going to be like, what? And then we're going to go to the theory. This says, let u equal 4i plus 2j and v equal negative 6i minus 3j. Decompose u into two vectors, u1 and u2, where u1 is parallel to v, and u2 is orthogonal to v. And then figure out what those are. Okay? Yeah, that's a little much, okay? So here's what we're going to do. For our background, okay? We're going to put our recall notes here, stuff that we are very sure of, okay? So we know that, how can I put this? What we just saw a minute ago was u dot v equals magnitude of u, magnitude of v, times the cosine of the included angle. I'm going to manipulate this slightly and solve for u, okay? So the magnitude of u is equal to u dot v divided by the magnitude of v cosine theta. So just isolating this term right here, I'm going to divide both sides by v cosine theta. Does that make sense, Nick? Why would I do such a thing? You'll find out in a minute. Okay, so now, a generic problem that looks like this. We have any generic u and any generic v and some angle theta in between the two of those. In this particular example, u, if we look at there, it's negative 4i plus 2j. It's in the second quadrant, and v is in the third quadrant. But it doesn't really matter where they happen to be. I could have a vector here and here, or here and here, or here and here, or here and here. Or here. It doesn't matter. I've just got two vectors, and there's some angle in between them. And what we want to do is split up u into two vectors. One of them, which two components. One which is parallel with v, and we want to call that u1. And then another part which is orthogonal or perpendicular, in a manner of speaking, to v. So u2. And some of the things that we can say is we can say that u1 plus u2 equals u. Haley, would you agree with that? u1 plus u2 equals u? Okay. What's more, we're going to focus here on u1. Alright? We could say that u1 is in the same direction as v. That's kind of what the idea them being parallel, right? Okay. If it's in the same direction as V, then we could also say this. Imagine, was it last week? We did that unit vector stuff. Remember the unit vector? The unit vector was a vector in the same direction as like V. But what is its magnitude? What is the magnitude of the one unit vector? Just one. But with magnitude of 1. So if I were to draw the unit vector for vector V, it would look something kind of exactly like this. I'll call it, what should I call it? A. There we go. Vector A. He's in the same direction as V. But what's his magnitude, Nick? 1. A vector with a unit with a length of 1 is kind of like the number 1. Okay? And that is, if you take any number and multiply it by 1, what do you get? So, Michaela, are we recording?
Yes.
Thank you. I was worried about that. So, if I take vector A and multiply it by the magnitude of U1, then I'm going to get a vector. I'm going to get itself. Okay. So, so U1 is in the same direction as as V, and U1 is in the same direction as we're calling this A, which is the unit vector. The unit vector for vector V. And we could say that U1, that vector, is equal to the magnitude of U1 times the direction of vector A. Okay? So let me say that again. So, U1, that whole entire vector is equal to whatever its magnitude is, maybe it's magnitude of 5, but in the direction of vector A. Okay? So like if A happened to be 2, 3, then it would be, but we reduce it to just that one unit length right there, like 1 over 2 and 1 over 3, then this would be a length of 30, but in the 2, 3 direction. Anyway, that's what this means. Okay? Further review. What is the formula for the unit vector? I think that was last week. It was the vector divided by the magnitude of itself. So we get U1 is equal to its magnitude times, this is the magnitude of the vector V divided by its magnitude. Okay? Now, we're building a case here. I am now going to take what I had over here, U dot V divided by magnitude of V cosine theta, and substitute it in for the magnitude of U1. So we're going to have U dot V divided by magnitude of V cosine theta times vector V divided by magnitude of vector V. Almost done here. I am now going to substitute in that dot product right there for this one right here. So I have u1 equals, instead of writing u dot v, I'll write magnitude of u, magnitude of v, cosine theta, divided by magnitude of v, cosine theta, times vector v divided by magnitude of vector v. So we've got cosine thetas which cancel. We have vector v that cancels, so we have u1 equals they don't want us to cancel the v's. Sorry. Just canceling the cosines. So u v over magnitude of v squared times vector v. Was that all? Yeah. And once I find u1, then I can say u2 equals, utilizing this formula, u minus u1. I'm not going to pretend that all made sense, but to everyone all the time. But if you have a question over it, you can ask me. That's fine. This is our end result. U1 is going to equal the dot product between u and v divided by the magnitude of v squared, and that we're going to multiply that times vector v, and then we're going to subtract those. Okay, let's get going. Here we've got u, and here we have v. So we're going to break it down into u1, which is going to equal u dot v divided by the magnitude of v times vector v. And vector v here we have, now this is, they have this as in ij form. I would prefer, if y'all are okay with it, just writing it in component form as like -6, comma, -3. Are y'all okay with that? Instead of writing -6i minus 3j, it's the same thing. John, we still good on that?
The raft is getting lifted, so.
So we can pause it?
Yeah.
Okay.
I don't think you put the wall. That's why there's like particles around the object.
Got you. Okay, we talked about that. Thanks. All right, so let's get going here. Dot product between u and v is going to be -4 times -6 plus a 2 times a -3. All over magnitude of v. So magnitude of v is going to be the square root of 36 squared plus, sorry, not 36 squared. Square root of 6 squared and 3 squared, so 36 plus 9. And we're going to take that and we're going to multiply that by -6(3). Let's go and look at our final answer, see if it has square roots and things like that in it. Okay, fraction. So, someone quick on the math here. 24 plus -6. So -18. Oh, just break it. Over 45, negative 6, negative 3. We did something wrong. The formula, it's just a minor thing, in the denominator is the magnitude squared, which is good for us. So it's going to be magnitude squared, which means magnitude squared, which means square root of 45 squared. So that's 18 over, well, square root of 45 squared is just going to be 45. So negative 6, negative 3. What is 18 over 45? 2 over 5? So we've got 2 over 5 times negative 6, negative 3. So that's going to be angle bracket 12 over, or sorry, negative 12 over 5, comma, negative 6 over 5. And then we can convert that into AI plus BJ form. We just say negative 12 over 5I minus 6 over 5J. And then for U2, we said that's equal to U minus U1. So U was negative 4I plus 2J. And then we're going to subtract from that what we got for U1, which is negative 12 over 5I minus 6 over 5J. So this second formula is so much faster, it's just literally subtract. So somebody help me out here, negative 4 minus a negative 12 over 5.
Negative 8 over 5.
And 2 minus a negative 6 over 5. This is 2 plus 6 over 5. 16 over 5. Okay? And so that's U2. Alright. So, notice what we did. U1 is the dot product between the two vectors. That's the numerator. Divided by the magnitude of the denominator squared. Okay? So the magnitude of V. What I want you all to do is on that paper is a table, work on question number 2. See if you can break it down and follow those steps to get that. And when you do that, then you'll be finished with this homework on paper. So I'm going to leave that up there, and I'm going to be walking around answering questions so that you can fight through it right now, get one answer good, and then for your homework you'll just be able to apply it 2 more times. Michaela, you can stop the video.